For 16.3, here's today's warm-up. It says let F be a vector field. That says for two distinct paths, C1 and C2, where they both start from some point P and both end at some point Q. Okay? It will never be possible that the line integral along path C1 will equal the line integral along path C2. Okay? Think about your knowledge of line integrals, whatever's there, and then just see if you agree with the statement or you disagree. Okay? If you agree with the statement, you agree that it will never be possible for these two to be equal. If you disagree with the statement, it means that you feel it might be possible. There could be two different paths that both have the same starting point and ending point. You have equality. Okay? Very open-ended question. But it just kind of has you guys assess, your understanding of line integrals to kind of have you guys review what we did before the exam on Tuesday. So think about it, and then as usual, pair up and discuss. I'll have you three here today. If Marco shows up, you can join Marco. I'll have you three here. You two as usual.
See why we have better like this. I guess they are like symmetrical.
So discuss with your group. See what you guys think.
Oh, it only shows like the relativity between the shell.
So that's an example of two paths that have the same starting and ending point. Okay?
Even the way you drew it, that'd be completely nonsense. Where you just create the same integral, so and that one thing could be anything.
Okay. Yeah, like something is just like coincident.
So we all
Yeah. I got a two extra points though. Like maybe some half R. Like before the maybe the same. And for some tricks for F.
All right, guys, about 1 more minute.
If you put the R into that, like what do you think?
can you grab
Yes.
All right, guys, I hear non-math conversations now, so let's see. let me see. We'll split the class in half right here, okay? So someone from this side of the class want to share what your group discussed.
Disagree?
Whatever your group discussed. You want to mention, do you guys disagree?
Yeah.
Okay, why do you guys disagree?
Like, suppose we have like symmetrical vector field and also symmetrical path that are like kind of. Yeah, so it just can be.
Okay, so you're saying that if there's like a symmetrical vector field and then the paths are symmetric.
And they follow direction. So, yeah.
And their flow would be kind of the same, right? Same. Okay,
Yes,
cool.
Yes.
All right, so you guys saying disagree. You're saying that it could be possible. Okay. All right, let me hear from this side of the room. What do you guys want to discuss? You also disagree? Okay. Okay. So you're saying whatever the path would be, you can create a vector field that can match kind of like the flow of this with the flow of that. Is that what you're saying? Okay, cool. All right. Anybody said agree? Most of you guys disagree? I'm gonna read your eyes on that one. Okay. It looks like most of you guys disagree. All right, so let's take a look. Let's see what happens. So good. So I'm having you guys remember that there is a relationship between the flow of the vector field and the orientation of the path. That's good. That's kind of what I wanted you guys to think about. So that's perfect. So we're going to start this section here with a theorem. Today's theme is theorems. So let's see, where's my black marker? All right, so section 16.3, the section itself is called the fundamental theorem of line integrals. Fundamental theorem of line integrals. All right, and so let me take you back to when did you learn the first fundamental theorem? Calculus, right? So in calculus 1, so in calc 1, we learn something called, the fundamental theorem of calculus. You learn 2. Most people remember the second one, not the first one. Fundamental theorem of calculus, part 2. And then remember what it said. It said that f is continuous on a closed interval a to b. Then, when you take the integral from a to b of the function, what did you do to evaluate that integral? Took the antiderivative, which the label is capital F, and then what did you do? You plugged in the terminal value into the antiderivative, and then you subtract it with what you get when you plug in the initial point. This guy you learned with Calc 1. And so there's a very similar theorem, which is this guy here, fundamental theorem of line integrals. So in vector calculus, that's what this is called, this chapter, in vector calculus, which is all about chapter 16, we use this theorem to get the fundamental theorem of line integrals. And then I'm just going to show you guys the quick proof of it. Okay? So we're going to use this to now make a theorem with line integrals that you guys learned last class. We're going to say let C be a smooth curve given by some vector function r of t, where, let's say, t varies from a to b. And then let's bring a function in. Let f be a differentiable function. Differentiable function where its gradient, del f, where its gradient is continuous on that curve. Let me stop with this. So we have a smooth curve that starts at t equals a, ends at t equals b. Okay? So here's where t equals a. And let's say this is where t equals b. Okay? This is your smooth curve. Okay. And there's a vector field. Pretend the board, the whiteboard is a vector field. There's all these vectors everywhere. So you guys, we discussed this in last week. The gradient is really a vector field. If we're calling the gradient vector. Remember that the gradient is the process. If it's a 2D function, or the 3 process if it's a 3D. So because it's a vector field, we can do a line integral on that vector field. We can take the line integral. You can use the vector field to take the line integral along that curve. And so what we end up getting using this theorem above is that, you know how you guys have to find the x function and the y function and throws it into the vector field at the beginning of the unit? So what this fundamental theorem of line integral says is, I'm going to get the ending point of my curve by plugging in b into the vector function, or the beginning of point, and you're going to plug that point into the function f, which is the function of the gradient. You get the term of the initial point, which is r of a, and then you plug that point into the function, and then you subtract those two values, and that's going to actually evaluate the line. Notice it looks very similar to this theorem. Right? There's just a couple more pieces are a little different. The discussion is a little bit different. Oh crap! I was sharing. This is screen. So you guys see this path that I drew here? What does this line integral really only depend on to evaluate it? This is the terminal point over here, right? This is the initial point. So what if I drew a path that looks like this? Like that. It still has the same initial point, and it still has the same terminal. So regardless of the path, this will still give you the same value because I'm just plugging in the terminal point, and then here I'm still plugging in the initial point. And so because those two paths have the same terminal and initial, the fundamental theorem of line integral says that this should just be the same. Okay? So relating to the warm-up, it is possible for them to be equal. Okay? I'm not going to have you guys prove this, but I do want to show you how it's proven, just for the folks that are like, oh my God, I love proofs. They get me all giddy. So let me show you here. So I did the proof in the case where it's a three-dimensional vector field. So you got a curve, a space curve with x, y, z, t functions. Your function f has partial f of x, f of y, f of z. And so if I want to compute that line integral, using the definition that you guys learned last week, I'm going to compose R into the vector field, the gradient vector field. That means that I'm plugging in these x, y, z's into the x, y, z's of these partial derivatives. Okay, I'm composing the R function into all those partials. Like that, times the derivative of R, which is just x, y, z prime. Take the dot product, you multiply this bad boy with this bad boy, plus partial of y with y prime, and so on. And you take the dot product, and then here's where the magic happens. So I want you guys to notice that this partial of f with respect to x is the partial of f with respect to x, right? X prime is the derivative of x with respect to t. Okay? Because you're composing you're composing R inside of the partials. Now the partials, which depend on x, y, z, through the composition, now they're all going to be in terms of t. Because you're composing them, right? So it's chain rule that ends up happening. So we have, if I do chain rule here, notice that's this path here, the derivative of x with respect to t times the partial of f with respect to x. That's this guy here. And then the same thing with y with this path, and then the same thing with y with z with this path. Okay? So that means that this dot product is actually just the derivative of the composition of R inside of F. This composition that we learned in chapter 14. And since I'm taking the integral, now back to calculus 1, this is a calc 1 integral. I'm taking the integral of the derivative of this function, right? The integral of the derivative of the function is the antiderivative evaluated at the endpoints. Since I'm integrating the derivative, the antiderivative is f of r of t. And so I evaluate it at the endpoints, which gives me the result. Yeah, and then in this equality, we can go from here to here because of this bad boy. Fundamental theorem of calculus. So I just wanted to show you that. I didn't expect you to do it, but you know, in case you want to nerd out, I just wanted to show you how that worked. Okay, so what I would like to do is I want us to do an example where we don't use the fundamental theorem of line integrals, and then do it with doing the fundamental theorem of line integrals. Because the theme of this week. Hold on, I'm getting ahead of myself. I'll tell you the theme of this week. Where was that? So excited. All right, let's see. So let's do this example. It'll say let's say it's a two-dimensional case, for the function f of xy equals to negative 2x plus 1/2 y squared, evaluate the line integral of its gradient vector field, where r of t is going to be cosine of t, comma sine of t, and we're going to have t range from 0 to pi over 2. So you guys remember this? You're parameterizing a circle, cosine and sine of t, but you're only doing it from 0 to pi over 2. You're only doing a fourth of the circle. That's the path. Circle of radius 1. That's the path, okay? This is one of that. This is a function, but we're integrating its gradient vector field. Okay, it's gradient vector field. So let's do this without, we're going to do it without the fundamental theorem of line integrals. We're going to do it the OG way, the way you guys did it on the homework. So we need to know what the gradient vector field is. So let's figure that out. Remember that you take the partials. This is partial with respect to x. This is partial with respect to y. So take the partial derivative of f with respect to x. What do we get? What do you get? Just -2. And what's the partial with respect to y?
1.
Just a good old y. Okay, so we have that. We already have our vector function r. So that means that let me not get ahead of myself. So if I want to do this line integral that I'm being asked to find, let's go back to the definition that you guys learned last week, 16.2. So it's the integral from t equals what to t equals what? 0 to pi over 2. And then we had to compose, you had to compose r inside of the vector field and then dot it with r prime. Okay. So let's see. Help me out here. All right, let's do the composition first. We're putting, this is the x function, this is the x of t function, and this is the y of t function. So remember, anything that has an x, you're going to replace it with cosine. Anything that has a y, you're going to replace it with sine of t. There are no x's, and the y here is just going to turn into sine of t. That's how we did the composition. Then we dot it with the derivative of r, which is the derivative of this guy here. What is that? Minus sine and cosine? Okay. dt. So let's see. Let me move it back a little bit. All right, take the dot product. We're going to get a negative times a negative is positive 2 sine t, and then plus sine t cosine t. T. And then we can do, I think we can just take a derivative from there. What's the antiderivative of positive sine? Negative cosine, good job. Negative cosine t, and then you could do a little bit of u sub here. Okay, you let u be sine of t, du is cosine t dt. Okay, so if you do a little bit of u sub here, you're going to get 1/2 u, which is really sine, squared of t. Okay? So that's the antiderivative of this bad boy. Now help me evaluate it from 0 to pi over 2. Yeah, that'll be what? 0? 0, 1/2. 0 plus 1/2 minus 2, and then 0. So it's 1/2 plus 2 is 5 over 2. That's how you did it in 16.2. Okay. Now let's do it by, since this is a gradient vector field, I can use the fundamental theorem of line integrals. So now let's do it with the fundamental theorem of line integrals. But before I do that, let me stop here. Anything you'd like me to repeat? Okay. Okay, so let's try it. So what do I need? Let's go straight into using the theorem here. So we have, this is our gradient vector field. But notice I don't even need to know what the gradient vector field is going to be. Because if I use the fundamental theorem of line integrals, I can just start by saying, okay, let me evaluate f at r of, it ends at pi over 2. So it's f at pi over 2 minus f composed with r of 0, where it starts. And let me show you how these are going to be the points. So you plug in pi over 2 here and here. What's cosine of pi over 2? 2. Here, I'll do them small and green. So it's going to be cosine pi over 2, sine of pi over 2. So notice that's going to be f of 0, 1. And then you're going to plug in 0 into cosine, 0 into sine. That's going to be 1, 0. So I know it's a little confusing to see that like this, because you're like, wait, what do you mean you're plugging in a vector function? But it's really the point. Okay? Then all we do is plug in those coordinates into this function, into what f equals. Okay? So it's going to be -2 times 0, because x is 0, plus 1/2 1 squared, minus -2 x is 1, plus 1/2 0 squared. And so notice that this goes to 0, that's a half, minus, what is that? -2. And we get the same answer. Okay? Which one would you prefer to do? This guy, right? It's crazy. You don't even need to know what the vector field is. That's kind of powerful, right? Here we needed to know it was that, but here this is saying that you don't even need to know that. Questions? Do you guys see how these are really just the points? Yeah, you will. So you're gonna, like I said, so there's gonna be like 6 theorems I'm gonna present to you. Okay. The things that I'm not, for example, validating, like your question, like to show it's continuous, is because all the homework problems are gonna have them be continuous, and anything I give you a test on will be continuous. Okay. And it'll be differentiable as well. Okay. There's going to be one theorem I'm going to present later where you can't assume the condition, so we will have to check that part, and I'll point that out when it comes. Yeah, but here the homework's going to give you all the functions will be continuous, and all the vector fields will have continuous pressures. Let me see, I have a picture here. Hold on. Okay, so let's see, this was, let me remind you the visual here. So there's 1, 2, 1, 2. So there was this point here, right? That was this point right here. That was the point 0, 1. Sorry, that's this point. And then there was this point here, which is 0, 1. So what we just did is we took the line integral along this path here. This is what we're calling C. Okay? And then there's a vector field described this way that has the vectors going all over the place. But as I was saying earlier with this picture, If you had a different path, like that, okay, this curve is still smooth. This curve is still smooth. So if I take the line integral along that smooth curve, I still just evaluate f at the endpoint and the terminal point. Sorry, and an initial point. So all this work would still be the same. I would still get phi hats. Okay. Cool, right? It's kind of surprising. Here, and here's the other thing that's surprising. You guys were saying I can create a vector field so that it flows with the same direction as this curve. This is saying it doesn't matter. That doesn't have to happen. The vector field could be it's this vector field, right? But this will still work. It's kind of like, whoa. All right? Yeah, James.
Kind of reminds me of differentiating between the physics concepts of distance versus displacement.
Gotcha. That's right. Yeah. Mm-hmm. Oh yeah, the distance you travel here is a lot different than this one, right? Mm-hmm. Okay, so yeah, so when that ends up happening with a vector field, where you just get the line integrals being the same, that's actually an important thing, and it has a little bit of vocabulary to it. So let me give you guys some vocab. Where's my markers? Okay, so let's do a little definition real quick. So we're going to say for a continuous vector field F with domain D, we say a line integral is path independent. It's path independent if you take a line integral along some path C1 for F, and it equals the line integral along another path C2 for any two distinct curves, C1 and C2, whose initial and terminal points are the same. Terminal points are the same. This definition is for a vector field, any vector field that has this condition, okay? This example that we've been playing with is a vector field that's a gradient vector field. Okay? But this could be, F can be a different vector field that's not a gradient vector field. But it's saying that if it has this property, we're going to say that this line integral will be path independent. No.
So if the vector field stays the same, the path doesn't matter at all?
Nope. Yeah, that's kind of a surprise. And the proof that we looked at, that's the math showing that it has to be true.
What about the situation if paths is not independent?
So, because there's so many theorems today, guys, there's a little bit of logic that's going to end up happening that's going to make your brain a little fuzzy. Let me go on. This won't be in the notes, okay? But it'll be in the video, okay? A lot of the statements we're going to do today are called if-then statements. Reticular linear algebra, you do this a lot as well. Okay? Where with logic, just the way variables are used to represent a math object, variables can be used to represent a statement. No. Okay. So if I call this statement P and this statement Q, the way I would write this with logic is if P is true, then Q is true. That is itself a different statement. It's a new statement. It's saying if this is true, then we're going to say it's path independent. Okay? Yeah. It's a bunch of conditions. Yeah, it's a bunch of conditions. The conditions for something to be path independent is this right here. For any two distinct curves. For any two distinct curves. Okay? So this statement's false. What do you guys think would make this statement false? What would have to happen for something to be, for it to not be path independent? No, not quite. It has to do with this word right here. That's right. If you can find two paths that have the same initial and terminal points that are distinct, if you can find a pair of two distinct paths that have the same starting and ending point, where these are not equal, the line integrals are not equal, boom, it fails, and it's not path independent. Because this has to be true for any two distinct curves. It has to always be true for any distinct curves. Okay? So this is in math called a for all statement. For all, meaning like for all this, it better be true. For a for all statement to be false, then there has to exist an instance that fails whatever condition it's saying. As long as there's one, then that for all statement is no longer true. Cool? Okay, I'll get to this in a little bit. So that's one thing. For this to be false, we need there to exist one instance of it failing. Yeah. We're going to look at other theorems, and I'm definitely going to give you an example. Yeah. The homework that you did, right? You guys had a bunch of 16.2. You had a bunch of different. You were doing a bunch of different line integrals. I'll get there. Yes. The answer is yes. I'll show you. Here, I think I'll explain this there when we get to it. But keep. There's a little bit of logic that's happening today that is very either fun or not fun, depending on your view. Okay. So we define what path independence is. You have a vector field, and no matter what path you take, it start and end the same. If it's always equal, it's path independent. So put this in blue. Because of the fundamental theorem of line integrals, all gradient vector fields produce path independent line integrals. Any line integral I do with a gradient vector field will have to be path independent because I just evaluated the endpoints, and all the paths are agreeing on the endpoints. All right, so then we have our next theorem, our next theorem. It says if F is some vector field, but if F is a conservative vector field, then all its line integrals are path independent. From what we discussed here with this, I want you just to, I'm gonna give you guys like 5 minutes, pair up with your group and convince yourself why this must be true. Okay? F is a conservative vector field, so therefore you're going to have to remember what that means. Why is it that they're always, the line integrals on conservative vector fields will always be path independent? You showed up a little late and you have homework, I'll go around. Give me your homework, please. Marco, did you get one of these?
Pretty sure.
All right, guys, help me out. What's a conservative vector field? What makes it conservative? What must happen? Has nothing to do with politics. That is where the vocab word comes from. Yes. If you're applying this stuff to physics, it has to do with that. But in terms of math, what if you? This is going to come up. This is the theme. This is where I was waiting for. This is going to be the theme of this week. Conservative vector fields. Okay. And what we're going to discuss right now at this moment is why we're going to make it a theme. What is a conservative vector field? What must be true? Yes, yeah. Is that what you're going to say?
I was going to say it always depends on the start and end points.
We'll see why though. We'll see why. But the definition of a conservative vector field has nothing to do with integration. You remember in 16.1, if f is a conservative vector field, then it must equal the gradient of some function. Okay? So because it's conservative, there must exist a function f where the vector field itself equals the gradient of f. That's what it means to be a conservative vector field. So for the rest of the semester, when we say conservative vector field, I need you guys to remember, okay, that means there exists a function f. When I take the gradient of it, it equals the vector field. Okay? So if f is a conservative vector field, it is a gradient vector field. So therefore, if I have two paths, and I want to take a line integral on them, right? F is really just the gradient then of this little f. So then, therefore, now what do I know I can do with this? Just do the theorem. Just apply the theorem, the fundamental theorem of line integrals. Right? So then, therefore, by the fundamental theorem of line integrals, I'll just evaluate the curve, the function at the initial and starting point. This is true for any two curves that start and end at the same 2 points. Okay? So this will always be true for any two paths whose initial and terminal points are the same. You guys convinced? Yeah. Okay. And when we did this, which method did you prefer? You preferred this method. Okay. Let's say the curve was a quadrilateral, like that, or not a quadrilateral. Let's just say it's this fucking shape here. Okay. So if I wanted to find, if I did not use the theorem and I asked you guys to do the line integral by definition, what you would have had to do is you would have had to parameterize this line segment. You would have had to parameterize this line segment. You would have had to parameterize this line segment. And then we learned from the properties of line integrals that to take the line integral of this whole thing, I had to do the line integral of this plus the line integral of that plus the line integral of that. You guys see how complicated that would have been? Okay, it would have been gnarly, right? But the fundamental theorem of line integral says you don't even have to do that. Just plug in the endpoints and you're done. So that tells us, oh man, the path can be scary. That's kind of funny. The path can be scary. Right. So you can go down a scary path. That's what I was trying to say. But the reason we care about conservative vector fields is because that means I don't even have to really take a line integral. I just have to do this for any conservative vector fields. And we want to do that. That'll be a lot faster. You guys see the power of that? It's kind of going to be a thing, okay? So for the rest of the class, we're going to figure out conditions to help us find a conservative vector field. Okay? All right. Today is very theory-based, not so much example-based or computation. Today will feel like an actual upper division math class. Okay, that's kind of how it feels. So hella theorems, and then you got to kind of connect the dots on your own. And then the professor goes hella fast. You have no time for group work sometimes. You leave, you're like, ah. So, but it's good to have a little bit of that. Okay. Let me go back to my other thing I was going to discuss. All right, so you guys see how this is an if, this, then that? Okay, so if you have an if something, then something else, we're going to call this a statement P and a statement Q. So in logic, we write it like this. An if-then statement is like a promise. If this happens, then I promise you that this has to happen. This must happen. Okay? So it's like a promise. If I give you this, then this must happen. That means that if I'm given P, I can conclude that I'm going to have Q also be true. Okay? What would break my promise? If there's an instance where hear different things. Say again?
P was true, but Q wasn't.
Yeah, that would suck, right? Like if I said, hey, if P is true, this better happen, and then then you find out that it didn't happen, you didn't have it. Oh, you broke your promise. Okay? So this is false when P is true and Q is false. Okay, that's what's going to make this false. Went down a rabbit hole. I gotta be careful. There's something in logic called a contrapositive, which is not the negation of this. Okay? So something called a contrapositive. You don't have to write this down because this is not what I'm going to test you. This is just if you know what's the logic behind this. A contrapositive is that Q is false will imply that P is false. So it's kind of like the opposite of the false. Okay? If this is false, then this will be false. Okay? It's not the false statement. Yeah, like this doesn't mean that this will be false. Okay? What ends up happening with logic is that if this statement's true, then this statement's also true. Let me give you an example with this. Okay? So if you're doing your homework and you find that a vector field is conservative, then you can conclude it's path independent. A contrapositive of that would be what?
If it's not path independent,
If it's not path independent,
it's not conservative vector field.
then we can conclude that it will not be a conservative vector field. Okay? Since this theorem says that this statement's true, the contrapositive is also true. Okay? So this theorem tells us that if f is not path independent, then f is not conservative. That's a nice little bonus there. Okay? All right, see that? I got one more definition and one more theorem. And then I'm going to have you guys play a little bit. And then I think we might take a break. Okay, so here's one more definition of something. What would happen if a curve's initial point and terminal point end up being the same point? Yeah? First, we're going to define what that means mathematically. We're going to say if a curve starts and ends at the same point, what do you guys think that will look like visually?
A loop.
It's a loop, right? But we're not going to call it a loop. We're going to say, we say the curve is a closed curve. Which, yes, it's a loop. So if I have a curve that looks like this, and ends up ending where it started, that's a closed curve. It doesn't have to be a circle. It can just be however it wants, but it just has to end where it started. Okay? All right. So through this definition here, we're going to see that. Here, let me just write it. Yeah, so here's the next theorem. For a vector field F, we're going to have what's called an equivalent statement. We're going to say line integrals of F are path independent if and only if, or it's equivalent to saying that the line integral of F will equal 0 for all closed curves. For all closed curves. Cool. Okay, for all closed curves. Okay. Let me give you a little intuition why it's tricky, like a little hand wavy proof. Let's say you have a closed curve, right? Let's say this is true. You have f, and you have that the line integral will be 0 for all closed curves. Let's say this is one of them. So then what you do, the trick is, you pick a random point on the curve. You say that this is the starting point, P, and this is the ending point. And you split the curve into two curves, C1 and C2. So now you have this curve, and now you have this curve. This is oriented this way, but I want this C2 to start here and end here, so I'll orient it this way. Okay? And because this line integral will equal 0, but notice that now I split this line integral into two separate line integrals. One with C1, one with C2. Okay? I think that's as far as I'm going to go. It's not too important for today's lecture, but if you're curious on proving this on your own, here's a way that you get started with that proof. Okay? And that's the kind of homework you guys get at the university level. To prove that theorem, and you gotta do it with your own creativity. That's the fun part. But don't worry, it's not too crucial to today's main theme. It's just a theorem that's gonna tell us that when is something path independent? Well, it'll be path independent when its line integral will always be 0 for all closed curves. And vice versa. Okay? If it's 0 for all closed curves, then it'll have to be path independent. All right, here's the fun part. I'm gonna have you guys do a little bit of logic thinking. Let me erase. Do you guys have the picture in your packet? Ah, yes, you do. Okay. So there, if you guys look at section 16.1 in your packet, 16.1. Let me open that up. Look at the vector field. Look at vector field 2. You see the one that's going in a circle? This one right here? With your group, just focus on that one. With your group, I want you guys to conclude if that vector field is conservative or not, using all this that we discussed. I want you guys to conclude if this vector field is conservative or not with your group, using the theorems and the discussion we just had. That one right there. So this one, I just wanted to show you which one in case you weren't sure, but I need you to see the theorems. Take a look at that. All right, let's see. Let me give you a hint. I want you guys to convince yourself why it's not conservative. Yeah? Convince yourself why the vector field is not conservative. Why is it not conservative? All right, guys, I got another hint. It's a circular vector field. Use that. Notice that it turns in circles. It flows in a circular way. Use your knowledge of line integrals that we discussed last week. How things flow. All right, guys. So remember, let's go back. Let's forget today, and let's just remember what you did in 16.2. Okay. Let's say you had a path. Let's say that it started here, and it rotated in a perfect. I can't talk. In a perfect circular shape like this. So it flows exactly with the motion of the vector field. What would be the line integral? What would happen if you take the line integral along that path? Should you get something that's positive, 0, or negative? Well, remember the line integral, remember when you got a number last week, you were thinking about, is the line flowing with the vector field? If it was flowing with the vector field, what kind of result were you supposed to get? You're supposed to get a positive result, because all those dot products, remember the way we're defining it, they're going to be positive. You add all those up, you get a positive answer. So if I create a closed path that's circular, so it flows along the vector field, it's going to have to be positive because it's flowing with the vector field. So if it's going to have to be positive, is this true? It's false. So therefore, this is false. And if that's false, then that's going to have to be not considered. No? That is the logic for it. Right? So that tells us something. That tells us that if a vector field has circular motion, can it be conservative? If any vector field that you find has a circular motion happening, we can make the same argument we just made. Create a closed path that goes along that circular motion. The line integral will not be 0. It will not be path independent, therefore. And if it's not path independent, it can't be conservative. Okay? So can a gradient vector field have circular motion? It cannot. Because then if it did, then you're saying that the vector field itself would not be conservative, but by definition it is conservative. Because it is a gradient vector field. So it's conservative. Okay. All right, let's take a breakdown. Math, right? Woo! All right, let's resume at 2:06. Okay. So we discussed the fundamental theorem of line integrals, path independence. Now we're going to talk about finding something called a potential function. Let me remind you what that is. We just did an example where you can figure out when a vector field is conservative. It's not conservative, sorry. Finding out when a vector field is conservative, though, can be a little challenging through the theorems that we just discussed. Because the only theorem that we discussed is if it's path independent, then it's conservative. But how the heck am I going to check that it's path independent? Because I have to consider all infinite paths to check that. That's not a good theorem to use to check for that. So the second part of class is we're going to call it finding conservative vector fields. Okay. And so here's a question. Is there some criteria that tells us when a vector field is conservative? When a vector field is conservative. And the answer is yes, with a theorem. See, I told you guys, I promised you a lot of theorems today. That Oprah meme, you get that, you get that. We all get theorems. That's today. All right, so here's what it's going to say. It's going to say let f be keep in mind, and please put this in your notes, this is two-dimensional. Okay, this is going to be for a two-dimensional vector field. Let F be a two-dimensional vector field with components P xy and Q xy. So let F be a vector field, defined. This is going to look a little scary, but we're going to talk about it. Defined on an open, simply connected domain D. We're going to discuss what the hell that was. What is this? What is open? What is simply connected? We'll talk about that in a little bit. Okay? So that's the criteria for this theorem. If there's a vector field, a two-dimensional vector field, on a open, simply connected domain, where P and Q have continuous partial derivatives, then we're going to have an equivalence here. We're going to have that F is conservative if and only if, here's where the magic comes in. You take the partial of P with respect to Y, and if it equals the partial of Q with respect to X, that's the criteria to tell us that we'll have the vector field being conservative. Okay? It's a little mysterious. Next Thursday, we're going to look at a bigger theorem that kind of also tells us why this will be true. Okay? It's kind of a bigger theorem. So what I want to talk about right now is I need you guys to understand what is open and what is simply connected, because that's part of the criteria. And as I was telling you, Marco, all the homework will have P and Q have continuous partial derivatives. That part will always be true. What you'll need to check is this part, okay, to see if something's open and simply connected. So let me discuss what that is. So open. What does it mean for a region to be open? Say it again. Kind of, yeah. So it doesn't contain its boundary. Doesn't contain a boundary. What I write here, guys, is like the informal definition of it. Okay, it's just for you guys to kind of get an idea of it. So let me show you an example, and then let me show you a non-example. So examples are like the entire two-dimensional space. All of it. It has no boundary. Let's say there's like some region like this. It does not contain its boundary. Okay, so it's open. Maybe something like an open interval that you guys learn in Calc 1. It doesn't contain no boundary points. And then the last example I want to give you is, let's say you graph something on the XY plane. Let's say it's like, here's 1. And let's say it's everything greater than 1. All points whose x coordinates have to be greater than 1, but not equal to. So it's all that left, that right side, but it has no boundary. Those are open. Something that is not open is maybe you have this bean looking shape here. It includes a boundary here, but then maybe it doesn't include the boundary like that. Or it could include its boundary all the way through. Okay. Contains a boundary, at least here it does, and this contains a boundary all the way around. As long as it has a boundary somewhere, it's not open. An interval like this, for example, is also not open. Okay. Have a better idea? Open? It just can't contain a boundary. Okay. Let's figure out what is a region that's connected. Let's go with connected first, and then we'll talk about what is simply connected. So connected. My informal definition to you is it's one piece. It's one piece. Okay, not the shell. It's one piece. Or another way of saying it, or another way of thinking about it, is that every 2 points can be connected by a curve. And then I'll show you guys examples of all that. Example, non-example. Recording, right? Yeah. Okay, so let's see. So an example could be like maybe I have some blob. Maybe there's a hole inside of it like this, and it's like that. However you want to draw your blob. Okay. If I pick any 2 points on that blue region, I can find a curve that connects them. Okay. Any 2 points that are on the region somewhere, here or here, there's a curve that will connect. Okay. So something like this. Maybe there's like a circle or a funky ellipse that is missing part of the boundary. This definition has nothing to do with the boundary. It just talks about the space itself. Is it connected or is it not? R2 itself, again, is also connected. Any 2 points in that space can be connected by a curve. Something that's not connected, visually you'll see it's like detached. It could be something like this, and then something like that. That is itself the whole space. If I pick a point here, and I pick a point here, now I can't find a curve that will connect them without going outside of the space itself. It's 2 pieces, right? It's not 1 piece. Let's do an XY plane kind of example. Let's say here's -1. Let's say here's 1. Contains this boundary. It does not contain this boundary. But then you have the entire right side, and then you have the entire left side. That. If I pick a point on the right side and I pick a point on the left side, there's never going to be a curve that will connect them without going outside of the space. Okay, sorry for all the vocab today. This chapter's a freaking doozy. Okay, so then let's see what simply connected is. That's connected. So simply connected is going to be a connected region with no holes. With no holes. Can't have any holes on that region. Example, non-example. So again, the entire R2 space, it's connected and it has no holes on it. The circle again, that's maybe missing its boundary. There's no holes and it's connected. This guy here, that I showed you guys earlier, one, let's say something like this. It's connected, it's one piece, and it has no holes. Yeah, Charlie. There's also, yeah, you can have a 3D region that's open and simply connected. That's Thursday. Yeah, we'll do that Thursday. We'll talk about that Thursday. This is just 2D. That's why I wanted you to put that there. All right, here I can have something like that, and then maybe there's a hole right there. So it's connected. Any 2 points can be connected in that region, but it has a hole. That won't work. This inequality one that I showed you guys earlier. And then one more. And then let's say you have the entire 2D space, but you're missing the origin. Let's say it's like literally the entire 2D space, but you don't have the origin. So why is this one not simply connected? There's a hole. Why is this one not simply connected? Is there a hole? It's not even connected to begin with. Okay, so this one is because of the hole. This one is because it's not even connected. It has to be connected to begin with. And then this one is because there's a hole. Okay? Okay, so what this theorem is saying is that we're going to want regions. Is this open? No. So that wouldn't work. Is this open? Yes. And it's simply connected. So we're going to want regions like this. And we're going to want like regions like R2. Or anything that's open, connected, with no holes on it. Okay? That's what this theorem, that's the condition. That's the part you'll have to actually check on the homework. Bless you. Okay. Questions on the vocab? Sorry for all the vocab. Yeah. So what I want to do is this theorem is going to be hella used for the rest of the semester. Okay. I want to show you guys 3 cases. I want to look at a vector field that satisfies the conditions, and then seeing if it'll be conservative or not by checking these this final condition. And then I want to look at an example where the conditions are not even met. So then what would happen with the theorem? Okay, I'm going to do the first one. I'm going to have you guys do the other 2. So let's look at these examples. So which vector field is conservative? So let me write them both down, or all 3 down, and then we'll do the first one as a class, and I'll have you guys do the last 2. Okay, so here's the first one. So F is going to be 3 plus 2xy, comma, x cubed minus 3y, sorry, x squared minus 3y squared. That's the first one. Second one is y over x minus 1 squared, comma, negative 1 over x minus 1. And then the third one is xy squared, and then minus x squared. Write those down. You have to erase the theorem. Okay. So let's do number one together. Number one, we got there was 3 plus 2xy, x squared minus 3y squared. All right, so what you're gonna have to do first, these are all gonna have continuous partials. Okay, the component functions will have continuous partials on their domain. So we have to check what the actual domain will be first. Okay. So first thing I want to do is check that the domain is open and simply connected. That's what I want to do first. This is P, this is Q. Any restrictions from P and Q for the domain? Just polynomials, right? So what's the domain of P and Q? Is just everything, right? All of R2. Okay. R2 is simply connected, and it does not have a boundary. So it's open and simply connected. Check. So now that I've checked my condition, now I need to use my theorem to check the partial of P with respect to which variable was it? With respect to y. So let's take the partial of P with respect to y. What do we get? 2x. And then check it with the partial of Q with respect to x. With respect to x, what is that? 2x. So since the partial of P with respect to y is equal to the partial of Q with respect to x, what does my theorem say? Theorem says f is what? Conservative. F is conservative. That's what my theorem would tell me. And that's what my question was asking me to determine. If my domain is not open and simply connected, and my partials were still equal, can I conclude something? No, because my condition of my theorem wasn't met, so nothing can be concluded. Okay? If my domain is open and simply connected, and these two are different, then what can you conclude? It's not conservative. Because this is what's called an equivalence statement. If this is true, this must be true. If this is false, this must be false. Okay? So let me have you guys do the other two and determine, see if you can determine if the vector field is conservative or not. And then just check with your group mates.
The last two can go domain one. So answer this domain. So I could have been checking the domain so that we can find then I can pass on by checking the two parts. If the parts are equal, then it's possible not equal. We can use it there. This would be, yeah, we usually don't forget to check the domain first, though, right? Yeah, I'll change it. Everyone's freaking out, sorry. It's because it was originally at that time, but I forgot what ended up happening. It was like a Monday or something, we had a holiday, yeah. Something happened, yeah, here, let me change it. No, earlier in the semester, I forgot, something happened. I had to change the calendar, so I moved the exam, but I forgot to change the date on Canvas, so let me change it. There you go. That's what it basically means that it could be true that these are not equal, but this guy will still be conservative. That's why we can't use the theorem, because that condition we can't use. For which part? This
For
part?
this whole assignment, I mean, to me, it seems that if you just look at it, okay, you have the domain as a whole, you go, so that one, okay.
You would not really. You just have to know what the domain is. But then the work, if it is open and simply connected, then the work would be this. To then use it there.
see. So this is what we got. Let's see. So if you check the domain of number 2, it's all points x, y that do not equal 1. Is it open? It has no boundary. It is open, but it's not connected. So then it's not open and simply connected. So because it's not connected, we can't conclude anything because we can't use the theorem. Okay? That's what I was chatting with you guys. That seems to be the what ended up happening there. For the second one, you check the domain. The domain is all of R2, which is open and simply connected. But if you check the partials, they are not equal to one another. And so therefore it is not conservative. Okay? Yeah, Chuck. Yeah, let me go back up to the theorem. Oh yeah, I erased it, so let me go back. The reason is because the theorem has 2 conditions. It's kind of like so you got pay me first and I'll let you in. Okay? So the payment is the conditions. So if your vector field is open and simply connected and the partials are continuous have continuous partial derivatives, if it's true, then you've made a payment. So then I can use this test. I can use this condition to see if it's met. If the conditions are not met, then I haven't made a payment, so I can't use the tool that the theorem is estimated. Meaning, it could be, if the condition's false, it could be that the vector field is conservative and these are not equal to themselves. So it's not trustworthy if the conditions are not met. Okay. So out of these 3, we have that this is conservative. You know, this one is. This one we don't know, we can't conclude. And this one we concluded that it's not conservative. Okay? So, since this one's conservative, what do we know? What does it mean to be conservative? Yeah, since this is conservative, we know there exists a function f such that that vector field will have to be the gradient of that little function. That's what all this is doing. Okay? That f has a name. We give it a name in 16.1. Starts with a P. That's called the potential function of the vector field. Okay? It's called the potential function. So what we're going to do now is, okay, part of this was I wanted to see if a vector field was conservative, and then now what we need to do is find its potential function. That way, if I have to integrate over this vector field, I need this little f to evaluate it at the endpoints. Okay? Remember, I'm tying you back to the beginning. That's kind of why we're doing all this. Okay. So for problem 1, this vector field, what was it? It's 3 plus 2xy, x squared minus 3y squared is conservative. So it has a potential function, little f, where the gradient of it equals the vector field. Okay? So therefore, the partial of it, the partials of it, of this little function, have to be equal to the vector field itself. Okay? So now the question is, what do you guys think? How do you think we're going to find f? Take it. That's right. We have the partial derivative. What we know is the partial derivative of this function with respect to x. Okay? This part here tells us that the partial is going to be equal to 3 plus 2xy, and the partial of y is x cubed, x squared minus 3y squared. Okay? So to find f, we use indefinite partial integration. Is that you said? Yeah. So the book, here's where I'm going to diverge a little bit different from the book. Okay? The book has its own technique of doing it. I'm going to do it a different way. You can go my way or the highway. So you can go my way or you can go the way the textbook does it. Okay? So since we know that these are the partials, I know that if I want to find f, I'm going to integrate the partial of f with respect to x. I'm going to integrate it though with respect to x. So to undo that, I'm going to undo the partial. So I'm going to undo I'm going to integrate the partial derivative with respect to x with respect to x. Okay? So partial integration, but indefinite. You're not evaluating at any endpoints. Okay? What's the antiderivative of 3 with respect to x? 3x. What's the antiderivative of 2xy with respect to x? Plus x squared y. And what did you normally do when you did plus c? But what's constant when you're taking the derivative of a function with respect to x? What are you treating as a constant? Y. That means that it's not just plus c. It could be plus some function of y, where it's only y. Some expression that only has y's on them. Okay? This is constant with respect to x. Or you could put, I think you said C1. Oh, yeah.
You have to write a partial of down moving the intervals partially.
Yes? This right here?
Yeah, no, I'm talking about the decimal.
This guy here?
It doesn't matter. Like how we go to partial derivatives.
Oh, no, it's dx. It's still the dx. Yeah, but yes, I see what you mean. Instead of doing the partial sign? Yeah, that partial sign is usually going to be used only for derivatives. Partial. Okay. Exactly, yeah. This is like, so it could be something like this. Let's just pretend. It could be something like y squared plus 5. That's constant when you're taking the derivative with respect to x, right? So it's just some function with y's and possibly just a constant. Okay, so what we know though is that my f for sure has this, and possibly a constant, and possibly just something with a y on. So then now let's do the same thing, but then let's do it with respect to y. Let's redo the same thing, the same process, but let's do it with respect to y. The partial integration of this function here, x squared minus 3y squared. We're going to integrate with respect to y. What's the antiderivative of x squared with respect to y? X squared y. What about this bad boy? Minus y cubed. And then a constant, right? But again, I'm integrating with respect to y. So the constant here is going to be some function with respect to x. Oh, let me not use the same one.
I know this is Thursday, but if it were more, would it be like h of xy?
Exactly. Yeah, that's what we're going to do with Thursday. So what you're going to do is you're going to use this. So therefore, you're going to look at the commonalities of these two results. Okay? Your f, notice this expression is in both of them because it has both an x and it has both a y. We know it has to have 3x. We know it has to have x squared y. Right? And what is this? What is this one here that this is showing us? Minus y cubed. That's the one that only has a 1. I could have instead say f is x squared y minus y cubed. And what is the h of x that this one has? It's the 3x, because that's the term that only has an x on it. Okay? And as Sam mentioned, your famous, it's possible that it has a constant. It's possible. So then we'll just still stick a plus c. So bless you. So this will be your potential function here. You're gonna compare the missing pieces basically. You're gonna include what you know your f has to have this, and you know your f has to have this. So then you include the missing pieces that this has, that this needs. Okay. Sorry, yeah. Exactly. Yep. The h of x is the 3x plus c. It's that and that. Or you can say that the g of y is the y minus y cubed plus c. Exactly, yeah. It's just a constant. We don't care what the constant is. The textbook does not do it this way, okay? So let's do a little summary. Okay. What do we need to do? You're going to be given a vector field. Then you're going to be asked, is it conservative or not? If it's conservative, you're going to use the theorem like you just did here. You're going to see, I use the theorem, it's telling me it's conservative. If it's conservative, then the homework will say, find its potential function. Okay? All right, so I have a little handout here for you guys where it's literally that. I'm giving you two vector fields. Then determine if it's conservative. If it is, find its potential function. I have one more problem in the back. And then I've created a concept map of all the theorems we did today. So you guys can see how they tie to one another. Huh? All right, that's it. Work this out. 1, 2, 3, 4. 1, 2, 3, 4. Check with your group mates. A lot of thinking today. I like it. Good job. No? Oops, sorry. Solutions to all these are posted in the notes, okay?
You want it's the portion of P with respect to Y. Okay. So, you can check the domain, so they don't match with the conclusion. So you do the domain. So this is the domain. That's what you can do English question. Cosine itself. He goes all the way. He goes all the way. That's the range. That's it. The domain itself. We have no restriction. This one right, this is that right. Oh, yeah, the rest of it. The sun, this is sun. So that goes between 1 and -1. So then that's the output. The domain and the graph what we can plug in. The graph goes on forever, and the graph goes on forever. So the domain is everything. Same thing with cosine. The graph is like this. And just like this. Anything that's negative, anything that's positive, anything that's positive. All right, guys, can I just have you check in with each other? Just confirm that you're getting similar kind of results. Just do a quick check. Quick check, guys. Just real quick.
What did you Oh, actually, I see what I did wrong right there. It's there. That was a Y. Yeah, and then they match up.
야, 이게 말이야. 사실 나도
Reset determine uncertainty. Find it.
And then you have to find the.
So you do
Yeah. And there's problem 2 on the back that I would like you guys to try. See what you got. Way easier, right? Any more questions? Beautiful. Look how fast that line is. Very fast. Mm-hmm. I believe that's the answer, yeah. Mm-hmm. Those are the points on the curve. The curve will look like that, right? And then when you plug in a value, it gives you that vector. So that's the point on the curve.
All right, guys, real quick for number 2, for 1B, for 1A, you'll find that the partials don't equal themselves, so it's not conservative. For part B, you'll find it is conservative. So you have your F here, you just write it down. Sine of y, e, there's no e anymore. And then you got e to the x plus x cosine y. Okay, so because it is conservative, that means that this bad boy here will have to equal the gradient of a potential function. So if you're getting a little confused, remember that you gotta maybe label this and remind yourself that this is the partial of x, that must equal the partial of y. Okay? That way you remember that this one you're gonna partial integrate with respect to which variable? You're going to do it with respect to x, because you're undoing the partial of x. You're undoing the partial of x, right? So when you're going to start integrating the first function, you got to remember that it's a partial of, it's supposed to equal the partial with respect to x. So you're going to undo that partial by integrating it. So you're going to take the partial of y e to the x plus sine y with respect to x. What did you guys get here? So, and then x sine y, and then some function of y, right? Okay. So then we do it again for partial with respect to y, and undo that partial by integrating it. So you're going to integrate the second function, e to the x. Is x cosine y. So the first function is that with respect to y, you're going to get y e to the x. X sine y, good. And now, yeah, so you got some function of x. And so the conversation I had with Charlie was, these both have the same terms and these both have the same terms. So that tells you that from here, there is no term that just has a y by itself. So what is g of y going to have to be only? Not 0, but just a constant itself. Just a constant. And same argument, this is supposed to be something with just x's on it, but that does not show up here. So again, this has to just be a constant. Exactly. So then therefore, f is just that plus c. X sine y plus c.
If we had an initial value, we could find c.
Yeah, they give you some conditions and things like that. There's ways that you can find c. And I'm going to stop there. We're done. We're going to finish early today. Okay? That went a lot better than I expected. 16.3 always scares me.
Wait, for question 2,